The learning objective of this section is to identify and describe the functions of the basic parts of a compound microscope. Just as there are many kinds of stereo microscopes, there are many kinds of compound microscopes. However, each of them has a base that supports the microscope and an arm that connects the base to the rest of the microscope. Although the stage of a stereo microscope is usually completely solid, the stage of a compound microscope has an opening, a hole, for light to pass through. Stage clips are often used on stereo or simple compound microscopes to hold a microscope slide on the stage and yet allow you to move it manually. In advanced compound microscopes, a mechanical stage is used to hold the microscope slide and move it from side to side and back to front. With the numbers on the side and back of the mechanical stage, you can repeatedly find the exact position of an object on a slide. A vernier scale allows references to 1/10 of a millimeter. All compound microscopes use transmitted light. Simple compound microscopes do not have a built-in light source. Light is directed to the lenses by a mirror. In this type of microscope, use the flat side of the mirror if you have a condenser and the concave side if you don't. Angle the mirror to evenly illuminate the field of view. If your microscope has an internal lamp, it is usually turned on and off with a sliding lever or a rotating knob. A condenser is a third optical component of a compound microscope. Its purpose is to gather diffuse light and concentrate or condense it into a narrow cone in the plane of the object. This improves the effectiveness of the objective lenses. A condenser may be fixed in position or movable with a knob. Generally, with the higher magnifications, a condenser is moved closer to the object. Closely associated with the condenser is a device for limiting the diameter of light entering the condenser. The usual mechanism is an iris diaphragm. An iris diaphragm consists of a set of thin overlapping metal leaves that can be moved by a lever to form a continuously adjustable aperture. Generally, the iris diaphragm is opened more widely with objective lenses with higher magnifications. Closing the iris diaphragm increases contrast. The iris diaphragm of the condenser should not be used to adjust the light intensity. Light intensity should be adjusted by decreasing the voltage to the lamp or adjusting an iris diaphragm on the lamp. Generally, with higher magnifications, you will have to increase the light intensity. There are two focus adjusting knobs on a compound microscope, a coarse adjustment knob and a fine adjustment knob. The coarse focusing knob always has a larger diameter than the fine. Use the coarse one first to get the objective approximately in focus, then use the fine one. The body of the microscope holds the lenses. Compound microscopes have 2 to 5 objective lenses mounted on a revolving nosepiece. Note that as the magnifications of the objective lenses increase, the physical lengths of the lenses increase. This causes the working distance, the space between the object and the objective lens, to decrease. In stereo microscopes, the working distance is very large, several centimeters. In compound microscopes, the working distance is very small, at most a few millimeters. Today's microscopes are usually designed so that the highest objective lenses cannot break regular slides. However, at higher magnifications, it is possible to break thicker slides. Such slides are usually called thick mounts. When using higher magnifications with such slides, focus the object by starting with the objective lens close to the slide and then move the lens away from the object. Higher objective lenses have smaller diameters and so smaller fields of view. So, before changing from a lower to higher magnification, position the object that you want to see in the center of the field of view. Good quality microscopes also have objective lenses that are parfocal with one another. Parfocal means that once you focused with the lowest magnification and switch objective lenses to higher magnifications, the object will remain in fairly good focus, perhaps needing only a minor adjustment of the fine focus knob. Compound microscopes can be monocular or binocular. Monocular microscopes have only one ocular lens, and so only one eye can be used to view the object. Still, to prevent eye strain when using a monocular microscope, both eyes should be kept open. Binocular microscopes have 2 ocular lenses. However, binocular compound microscopes have only one objective lens that can be used at one time, and so the image is only 2-dimensional. Stereo microscopes are all binocular because they must have 2 ocular as well as 2 objective lenses to create 3-dimensional or stereoscopic images. To make compound microscopes easier to use, most have inclined objective tubes. However, some older models have an arm and stage tilt mechanism. This is okay to use with prepared slides, but it is not very useful for wet mounts. Especially in compound microscopes, there may be a pointing device in one of the ocular lenses. Students and teachers use such pointers to help communicate with each other about what is being observed. Ocular lenses may also have a measuring device, often called the ocular micrometer. This will be discussed later in this video. Binocular compound microscopes have an interpupillary adjustment mechanism similar to stereo microscopes. Such compound microscopes also have a diopter adjustment mechanism. The learning objective of this section was to identify and describe the functions of the basic parts of a compound microscope, including base, stage, arm, body, coarse and fine focusing knobs, objective lenses, which are located on a nosepiece, ocular lenses, diopter adjustment, interpupillary adjustment, condenser, iris diaphragm, and lamp adjustments.